Okay, so let's take a look at question 1a. This one's worth 3 marks. The question is, the following table has either the binary or denary value of 3 numbers. Complete the table by converting the 8-bit binary number into denary and the denary number into 8-bit binary. So we're just converting from one to the other. Just as a point of reference here, though, we are converting into 8-bit binary. So we do need to make sure that this field here, when we fill it in, is in 8-bit. So let's have a look then. What we need to do is create a table first of all here, which I've done. And all we're going to do is wherever we've got a 1, we're going to add up the corresponding numbers that are above. So we can see for this first example here, we're going to add 128 because we've got a 1 underneath that, with 64, with 32, with 16. And if we add all those numbers together, that gives us 240, which is our first answer. The next thing we need to do is do it the other way around. So we're trying to make 105 using a combination of these numbers here. It's an odd number, so we know we're going to need a 1 at the end. So that's a good way to just quickly check. But we're going to start with the largest numbers first. 128 is too big, so we can't use that one. We're going to need 164 in there. 64 add 32 is 96. So we know now if we're on 96 and we need to try and make 105, we only need another 9. So we can make 8 and 1 to make our 9. And then we can put a 0 in everywhere else. So the correct answer there is 0, 1, 1, 0, 1, 0, 0, 1. And the final one we've got here is 0, 0, 0, 1, 1, 1, 1, 0. And this is exactly the same as the first answer. All we're going to do is add 2 to 4 to 8 to 16. If we add all those together, so 16 plus 8 is 24, plus 4 is 28, plus 2 is 30. So the third answer there is 30. Okay, let's have a look at question 1b. This is worth 4 marks, and the question states, complete the table by writing the answer to each statement. So we've got 4 statements down the left-hand side here, and all we need to do is write an answer in the box provided on the right. So the first statement says, the smallest denary number that can be represented by a 4-bit binary number. Well, we know without doing any kind of calculations that the smallest number we can get is going to be 0. And this is if all of the numbers here, all the different bits are off, they're all set to 0. So let's just pop this on here and we can see as an example that we've got 4 bits. So this is a 4-bit binary number here. And we can see if all of those are set to 0, then the smallest denary number we could get if we were to convert this, we don't have any 1s, any 2s, any 4s, or any 8s, would be 0. So we can see here in the mark scheme that the correct answer for that one is 0. Second statement says the largest denary number that can be represented by a 6-bit binary number. So let's change this around a little bit and we'll add 2 more bits. So now we've got 6 bits and we're trying to make the largest denary number. So essentially what we're saying here is if all of these were 1, what would the largest number be? So if we add 32 to 16, we get 48. Add 8 is 56, 60, 62, 63. Another quick way of remembering this is you can look at the next bit above and you can minus 1 from it, and that will give us the right amount of combinations we can have as well. So you could do it either of those methods. And the next question is a bit of a tricky one. It's trying to throw a bit of a curveball here. So it says the maximum number of different colors that can be represented with a color depth of 7 bits. Okay, so we've got 7 bits here. And if we popped the 1 in there, we follow the rule from the previous question. We know that if all of these are set to 1, then it's this number here minus 1. So we know that all of these together here, if all of these 7 bits are 1, it would give us 127, which I think a lot of people will probably put down as the correct answer. But they're forgetting that all of these can also be off as a final color, okay, which might be represented as black, for example. And that gives us 1 additional combination. So we can make up to 127 here using these 7 bits, but we can also make 0. So we take 127 and we add 1 to it with our zeros, and that gives us 128 different combinations. The final question says the minimum number of bits needed to represent 150 different characters in a character set. So we're essentially trying to make 150 using this table here. So to make 150, well, we can't do it using these 7 bits because that only goes up to 127. So we need that 8th bit in there. So we'll be using 128. So we need to make an extra 22. So let's make 16 and 4, and that gives us 20, and then 1 for the 2. So we know that we need to use all of these 8 bits to make or represent 150 different characters in a character set. Question 1C is worth 1 mark, and it says, show the result of a left binary shift of 4 places on the binary number 0000 1111. So the key points to take out of this are left and 4 places. Okay, so here's our number here on this top row, and we're going to take each number and we're going to shift it 4 places to the left. Okay, so if we start over here, we can see that if we take this 1 here and we shift it 4 places to the left, 1 gets moved over there. Likewise with the next one, it gets moved over there. Hopefully you can see a pattern emerging here. Okay, and the rules of the binary shift state that we need to fill the empty cells in with zeros. So our result therefore is 1111 0000, which you can see is the correct answer on the mark scheme. Okay, so let's have a look at question 1D. It's getting a little bit trickier now. This question is asking us to describe how to convert a 2-digit hexadecimal number into denary, and we need to use an example in the answer. So if we have a look at the mark scheme on the right here, there are 2 different methods we can use to do this. I'll go through them both, but we do need to include a correct example here to be able to get that 3rd mark. If you don't describe them properly and you do a worked example, you can still get marks for your kind of working out your method marks, but you won't get a mark for the correct answer. So let's have a look at the first method here. So we'll look at the converting one. So if we convert each digit into 8-bit binary and then combine them into 8-bit binary and then to denary. Okay, so let's have a look at this table. Okay, so we know hexadecimal is base 16, so there's 16 unique values. And we know that hexadecimal and denary are exactly the same from 0 to 9. And then beyond 9, when denary goes from 10 up to 15, hexadecimal goes into the letters, so A to F. So really we've got 0 to F in our hexadecimal number system. So let's take an example. If we do, let's do A5. So if we take A5 as our worked example here, okay, and if we're doing the converting here, we need to convert each digit into 4-bit binary. Okay, so we're going to convert A first of all into 4-bit binary using this table here, and we can see that A is equal to 10. Okay, so we're going to make 10 out of binary here, and to make 10 we need 1 8 and 1 2. Okay, so there is our A, and then we need to make 5 on our second 4-bit binary, which is going to be 4 and 1. And then we need to put these into an 8-bit binary to be able to convert this hexadecimal, 2-digit hexadecimal into denary. So let's take the A first of all. So we've got 1 0 1 0, 1 0 1 0, and if we take the 5, we've got 0 1 0 1. And then all we need to do is a little bit of maths to be able to solve this. So we're going to do 128 add 32, which is 160, add 4, which is 164, add 1, which equals 165. Okay, so if we were to show something like this, if we were to describe that we need to convert each digit into 4-bit binary and then convert to 8-bit binary and then to denary, if we had something like this down on the paper that and a worked example, then that would show that correctly and you'd be getting all 3 marks. And the second method we're going to look at is multiplying. So we can see the 2 bullet points here in the mark scheme. Multiply the left or the first digit by 16 and then add the value of the second digit. This is a lot more straightforward and simpler, and it will probably take less to show this method on your paper, so it will save you a bit of time as well. So let's take the first, or the same example, sorry, that we used in the previous example. So we're going to have 8, 5 in this. So we know that A is equal to 10. So A equals 10, and obviously 5 equals 5 in denary. So we take the 10 and we multiply it by 16, and we get 160. And then all we need to do now is add on the 5 equals 165. So that would be a lot easier to do it this method rather than using the multiplying method, the converting method using a 4-bit binary and then converting into 8-bit binary and then converting into denary. So this method would be more preferable, but whichever one works for you. Right, question 1E is worth 2 marks, and the question says, add these two 8-bit binary numbers using binary addition and show your working out. So there's 2 marks available for this. The first mark is for getting the correct answer, and the second mark is for getting the correct carries in the correct position. Okay, so 2 marks in total. For this one, we need to be familiar with the rules of binary addition. Okay, so if we've got 2 zeros, the result is a 0. 0 plus 1 is a 1. 1 plus 0 is a 1. 1 plus 1 is a 0, and we carry a 1. And then 1 plus 1 plus 1 is a 1, and we carry a 1. So I've just created this little diagram here for you so we can work through this. So 1 plus 1, let's have a look at our rules. It's 0, carry 1. We put that in the right position. And then we've got a 1 plus 1 plus 1, which is 1, carry 1. And then we've got a 0, a 1, and a 1. So that is going to be 2 1s. So it's a 0, carry 1. And then we've got 3 1s, which we know is a 1, carry 1. And then we've got 0 plus 0, which is 0, plus a 1 is going to be 1. And we've got 1 plus 0, which is 1, 1 plus 0, which is 1, and 0 plus 0, which is 0. So if we check that against the mark scheme, we've got 0, 1, 1, 1, 1, so 0 and 4 1s, and then 0, 1, 0, and we can see we've got 4 carry bits, and they're all in the right position. So 1 mark for this correct answer here, and then 1 mark for having your carry bits in the correct place. Question 2AI is worth 2 marks, and this scenario that you're given here for the questions that come after this are talking about an airport. So it says an airport has computers that are connected together on a local area network, or a LAN. Each computer has an IP address and a MAC address. Give 1 valid example of an IP version 4 address and 1 valid example of an IP version 6 address. I think the thing that people fall down on this is they have a look at an IP version 4 address and they know an example of an IP version 4 address, and then they kind of take the 4 in IP version 4 and think, well, an IP version 4 address is split up into 4 groups. Therefore, an IP version 6 address will be split up into 6 groups, when it's not actually the case. The IP version 6 is split up into 8 groups, and it uses hexadecimal and is separated by colons. So let's write an example of an IP version 4 address. The standard network address, which will be the network address of your router at home, would be something like 192.168.0.1. That's kind of a standard local area network address, which you could use. You could also use Google's address that we've looked at in lessons times is 8.8.8.8. Basically, all we're looking for here is 4 groups of numbers. The numbers need to be between 0 and 255 and separated by full stops, and that will get you a mark for that one. IP version 6, as we've just determined, we've got 8 groups of hexadecimal numbers separated by colons. So we could, for example, do 2A, colon 2A, colon 2A, colon, etc. until we've got 8 separate groups. 6, 7, 8. Okay, and that would give us a valid IP version 6 example for that one too. Okay, question 2AII is worth 2 marks, and now we're being asked to describe the format of a MAC address. This is where a lot of students were getting confused with that of the previous question. So you've got the IP version 4 and IP version 6 in the previous question, and students look at the IP version 4 and think, all right, it's in 4 groups, therefore IP version 4 is in 4 groups, and that must mean that IP version 6 needs to be in 6 groups, which is not the case. IP version 6 is in 8 groups, and it's the MAC address that's actually in the 6 groups. So what we need to do here, because it's a describe question, and we can give a written example as well, but we're describing what are the characteristics that make up this MAC address. So we can say that it's presented in hexadecimal, denary, or binary. It has 6 groups of numbers, or 12 hexadecimal numbers, and each group has a paired 2-digit hex numbers, or an 8-bit binary number, and it's separated by colons and hyphens. So let's write down an example. We'll use a similar kind of a hexadecimal that we used in the previous one. So all we need to do here is say 2F, for example, is an example of a hexadecimal. And we know that this is separated by colons or hyphens. And we know that it is also in 6 groups. So there we've got 6 groups of hexadecimal. We could also say, because we know that the MAC address is made up of 2 parts, or it can be split into 2 parts, and the first part contains the manufacturer ID, so the company that made the device, and the second part contains the serial number, which is unique to that individual device. As we know, MAC addresses are completely unique the world over. There are no 2 devices that share the same MAC address. So an example and a description there would have got you both marks. Okay, question 2BI. This one's worth 4 marks. Again, we're still in the airport scenario. So the airport currently has wired connections in their LAN. Describe 2 benefits to the airport of using wired connections in their network. So this is advantages of a wired network. And the thing that students miss on this particular question is that they don't apply their answer in the context of the airport, because it's asking for 2 benefits to the airport, not just 2 benefits of wired connections, which I'm sure we could all write lots on, 2 benefits to the airport. So we need to say what the benefit of the wired connection is, and then state how that is a benefit for the network. Okay, so we've got some examples down here in the mark scheme. Let's go over the first example. So the one that most students say, first of all, is speed. So we could say that wired connections have a faster speed. Okay, that is 1 mark, because that is a benefit of wired connections. We could even say than wireless connections. This is a benefit to the airport, and then we could say why that's a benefit for the airport. Because faster speeds mean less delays at the check-in counter. Okay, so that would be perfect. 2 marks, 1 mark for this part here, saying what the benefit is, and then 1 mark for saying how it's a benefit to the airport. We can also see here on the right-hand side that we can only get a maximum of 3 marks if we're not talking about the context of the airport. So we need to make sure we're doing it in the context of the airport. Okay, so point 2, we could talk about the fact that wired connections have less interference of objects than wireless connections. Okay, so we've put another point in there that wired connections are the more reliable. There's less interference, things like walls getting in the way of your wireless signal. And then we need to state how that would be a benefit to the airport. So we could say this is a benefit to the airport because data can be transferred around more reliably without data getting lost or delayed. Okay, so we've said what the benefits are, and then we've said how that is a benefit to the airport in the correct context. Okay. Question 2BII, this one's worth 3 marks, and again we're still in the airport scenario. Explain the reasons why the airport should also allow the network to be accessed using a wireless connection. So the previous question we were looking at advantages of a wired connection. Now we're looking at advantages of a wireless connection in the context of an airport. And these questions are quite straightforward to put yourself in that situation. If you imagine yourself being at an airport, I'm sure we'll have in the waiting room waiting for a flight. If you didn't have Wi-Fi, if you didn't have a wireless connection available at that airport, what would the disruption to you be? How would it be more difficult for you to do what you need to do? And if you think about your parents, for example, checking kind of flight information and having the tickets and that kind of stuff on their mobile phones. If you didn't have access to that, what would the effect be? Also think about the staff at the airport. We can talk about staff and the passengers at the airport here. What do staff need to do as they're moving around the airport, the people who work there? So that's kind of what we're looking at here. We're trying to think of advantages for the customers and for the people that work at the airport. It's a 3-mark question, so we're going to try and explain 3 different reasons why allowing a wireless connection will be a benefit to an airport. So let's have a look at a model answer then. So we could say the airport should also get a wireless connection because, and then we can pick some of the reasons here up in the mark scheme. We know that it's a lot easier to add new devices. Okay, all you need to do is hop on your phone, go to your wireless settings, and then select the network, and then you're connected. Whereas if that was a wired network, we'd have to actually get a laptop or something that's got an Ethernet port on it. We'd need to get a cable. We'd need to find a space in the wall to be able to plug it in. Okay, so we know that it's easier to add new devices to the wireless network. Okay, so that would be a first point. We could also say here that it would also allow staff to be more mobile, so they can move around different parts of the airport and still access important information on their devices. Okay, so that's 2 points, so that would be 2 marks. And we could also, you've got here, we can talk about the advantages of wireless. It also says that we can allow the reverse, so we could talk about how wired networks restrict as well. So for this one, we could say whereas with a wired connection, the staff would need to remain in one place and be, say, tethered or connected by a network cable at all times. Okay, so you can see we've got 3 different points there. We've talked about the staff, and we've talked about people being able to get access to the network more easily, and to add devices as well. So that would be a 3-mark answer. Question 2CI is getting us to do a little bit of artwork. So the scenario, again, in the airport says one office in the airport has 5 computers connected to 1 switch, and there are 2 printers in the office that can be accessed by all computers. The computers are connected using a star topology. Draw a diagram to show how the 5 computers, 1 switch, and 2 printers are connected in a star topology. Okay, so you should know that in the center of a star topology is the switch. So we're going to put the switch in the center here, and these need to be correctly labeled. Okay, it's really important that they are labeled. You can't draw a picture that looks like a computer and have that marked as a computer. So it does need to be labeled correctly. You can have something like S for this, and then in the bottom corner you could write S equals switch, C equals computer, P equals printer. That is absolutely fine. You can draw a picture and then put a line off it and then write switch or computer. But I would recommend just literally doing it like this. You don't need to draw pictures. You can just have the words. The thing that we're trying to get right here is that there is 1 switch, and we know with a star topology network, the switch is the thing that sits in the middle of it. It's not a server. We don't need to add a server to this at all. Okay, it's just a switch. It's just a device that is going to direct the data packets to the correct destinations from one node or one device to the other. So the switch sits in the middle. And again, let's have a look back at the question. We know we've got 5 computers, so we could put the 5 computers in here. And we also know that we've got 2 printers. And then we're just putting them around in the star topology. Remember, the switch is in the center. And then we put devices around them. And then all we need to do now is connect them up. So we'll just use some lines. Don't need to put any arrows on these or anything. Fairly straightforward, nice, simple diagram. And that should be for our 3 marks. So first mark is for 5 computers, which we have, 2 printers and 1 switch clearly labeled, which they are. All devices directly connected to the switch, which they are. Only 8 devices and no additional connections other than to the switch, okay, which we have here as well. So if you were to put a server in here, then you wouldn't actually get that 3rd mark because it's asking for just 8 devices and no additional connections. So we need to make sure that that server isn't in there at all. Let's move on to question 2CII. This question's worth 2 marks. We're still on the subject of network topologies. And this question states, give 1 benefit and 1 drawback of the office using a star topology instead of a mesh topology. So we're trying to think of 1 advantage of having our network set up like this in the star topology as opposed to a mesh, and 1 drawback of having it set up like this as well. So I've just copy and pasted the star topology picture that we used from the previous question, and we're trying to think of 1 benefit of this, and we've got some benefits up here in the mark scheme. So to add a new node would actually be quite straightforward. Let's say we wanted to add an additional printer here. We could just get a new printer and we could put buy a cable and connect that straight up, and it's really easy to add a new node. If that was a mesh network, and we remember from a mesh network, this computer here, for example, might be connected to each of these other devices. We remove the switch with a cable. So this computer here might need 1, 2, 3, 4, 5, 6, 7 additional cables to connect it to all of the other computers. Okay, so that would be a benefit, that it's easier to add new nodes or new devices to this one. We've also got here an advantage of a star topology. The central device can monitor and control transmissions. So the switch's main purpose here is to control data transmissions between these different nodes or devices. It means it's faster because the switch does a very good job of moving those packets around to their correct destination. It also means there's fewer data collisions because all the devices aren't connected to each other. They're all connected to the switch. And 1 connection or computer breaks, the network still works. So if we were to say, let's say we've got a problem with this computer here and the connection breaks, all of the other devices or nodes that are connected to the switch, they still operate, they still work. Whereas if we've got a mesh or a partial mesh network where this computer or some connections go through this computer first and then to the printer, if this computer breaks, then we're not able to access this computer either. There's also less cost of cables in a star topology because you can see we only need 1 cable plugging into the switch for each of the devices, whereas if it was a mesh, then this computer would again be connected to all of the 7 other devices that we've got here, so extra cables needed. Less cost on its own though, we can see cheaper on its own or speed on its own is not enough. So any means not enough. We need to state why that is. So less cost because of the cables, the amount of cables that you need to purchase. Okay. So there's some advantages with that one. The drawback, the obvious drawback here is we are heavily reliant on this switch to be functioning correctly because its job is to transmit the data packets around to the correct destinations. And if this went down, then we wouldn't be able to access anything at all because there are no live connections from any of these devices, any of these nodes to each other. So it has a central point of failure, a single point of failure. Another drawback is that the switch does cost money. So you could say extra cost because of the switch or the central device. Okay, again, not just it could cost more. We need to say why it's going to cost more. And they're your 2 marks. Right, so question 2CII is worth 3 marks, and it's asking us to describe the role of the switch in the star topology. And I've continued with this image that we used from the previous questions, just to show you what the star topology looks like. As we recall, the switch is in the middle and all of these devices or nodes are connected to the central switch. This question really is about talking about what this particular or what the job is of the switch, this particular device that's in the middle of this star topology. Okay, so we've got quite a few points here. It's a 3-mark question, so we're going to write 3 points down here. Now, we know that the switch's job is to connect all of these devices together in a network. If the switch wasn't there, these computers and printers, the peripherals, wouldn't be able to communicate with each other. So it's the switch's job to connect them all together. And we know from the previous question, if this switch wasn't here, then none of the computers or devices will be able to communicate with each other. So the first point that we could say here is the role of the switch is to connect all the devices together to form a network. We could also say that this lets the devices communicate with each other. Okay, so even though that's 2 sentences, this is in with the same mark point here, but I've just elaborated on it slightly. We know that the switch is going to receive data from all of these devices. Okay, so when a computer needs to send a bit of information to another computer, the switch's job is to receive that data. The switch then will, using its intelligence, be able to find the correct computer that it wants to send it to. Okay, so it's about receiving data and then passing that data on to the correct destination. So we could say here the switch is also responsible for receiving, nor my spelling, data from all the devices in the star topology and directing that data to the correct destination. Okay, so we've got 3 points in there. We've got the role of the switches to connect the devices together, which is mark point 1 up here, that lets the devices communicate with each other. The switch is responsible for receiving data, which is mark point 2, and then directing that data to the correct destination, which is down here at mark point 6. We could also add on an extra one onto this just to be doubly sure that we've got the right answer. We could say the switch uses the MAC addresses of the devices to do this, and that fits in with mark point 5 here, uses MAC addresses. Okay, so we've actually got 4 points down there for a 3-mark question, just in case we get an examiner that is a little bit picky with how we've worded things on that answer. Okay, some other points that we could get here are that the switch records or stores the address of the devices connected to it in a table, so it knows where to send them to. And also, if the address isn't recorded, so if a device sends a piece of data to the switch and it doesn't know where it's going, then the switch can transmit that data to all devices to see which one is due to receive it. So 2 extra points we could get in there for that one too. And question 3A is worth 4 marks. This question is stating that a computer has an operating system and utility software. It gives us a table that contains operating system functions, and then it gives us the task of each of those functions. We need to complete the table by writing in the 2 missing functions on the left-hand side and the tasks performed by the 2 given functions here on the right-hand side. Okay, so this one really is about functions of an operating system, of which they are 5. The only one that's not included in this question is user management. So actually making accounts, or the operating system is obviously responsible for making multiple accounts on a computer. So you could set up one with admin access for yourself, and you could set up one that doesn't have admin access for your younger sibling, for example, if you don't want them messing with your computer. That particular part is not involved in this question at all. So the first one, we're given the task, moves data from secondary storage to RAM. Okay, so this is taking something, for example, if you open up an app that is stored on your hard drive, and because you've opened that RAM, it needs to copy it from your hard drive into, you've opened up that app, it copies it from the hard drive to your RAM because it becomes in use. And remember, RAM is memory that's used to store apps or programs instructions that are currently in use. And that is the job of the memory management part of the operating system, because it's dealing with memory. It's moving data from one place to another. Okay, so memory management should be the function for this top one. Peripheral management, this is the management of things like mouses or keyboards or anything that's plugged into the computer. And we've talked about in the past how each of these devices, so your mouse and your keyboard, when you plug it in for the first time, it needs something called a device driver. Usually Windows or what operating system you're using will go and download this itself. Sometimes you need to go onto a particular website and download it yourself. When you install a new graphics card, for example, you might need to go and get that particular device driver for that graphics card. So this is what peripheral management's doing. Peripheral, remember, means kind of on the edge of. So your peripheral vision is on the outside of your eyes. Peripheral device is on the outside of your computer, so things that are plugged into it. And this is responsible for receiving data from an input device, so receiving data from your keyboard or from your mouse, transmitting data to output devices, for example, to some speakers that you might have plugged in, installing or downloading device drivers that actually allow you to use those peripherals, and it allows communication from your input device to output device, so communication between, let's say, a mouse to your computer screen, for example. So that's managing the peripherals. And the third row down we're looking at here allows the user to create, name, and delete folders. This is something you do in Windows Explorer, so the yellow folder at the bottom of your screen at the moment, and this is to do with file management. So the answer for this one is file management. And finally, the operating system is responsible for providing a user interface, and the user interface allows you, the user, to interact with your computer. So it allows us to interact with the graphics, the graphical user interface, so the icons that we click. It allows us to communicate with other aspects of the computer. It allows us to receive inputs from the user, so using the mouse or the cursor, for example, and it can also output data to the user as well. Okay, so the best answer here is it allows the user to interact with the computer. Okay, so hopefully that's explained that question. So it's quite a tricky one for 4 marks. Okay, question 3B is a 6-mark question, and it's a fill in the blanks question. And we're given a table of words there, keywords, and all we need to do is put them into the right place in the sentences given below. So it says, complete the description of utility system software using the words provided in the box. Not all words are used. So it's quite hard on this question to decipher what it is that this first paragraph, this first couple of sentences is actually talking about. So we need to try and get some clues out of this one to see what it is. So it says something software changes data using a something. Now, if we just take that sentence in itself, we're not going to be able to fill it in using these words. We need to go a bit further down to see what the context is of the question. So it says if the data changed is intercepted, it cannot be something. This software does not stop the data from being intercepted. So we're talking about data that's being stolen, that's being intercepted. Okay, that's maybe being plucked out of the air. The packets are being plucked out of the air by a hacker, for example. So we know that we're talking about system security here. So we're thinking about software that changes data, that changes the way that data looks so it cannot be intercepted. And from that, you should be able to decipher that this is actually talking about encryption. Okay, so the scrambling of data as you send it from your computer. So as it gets sent to the receiver or the correct destination, people can't just steal that data and have a look at it and read it. So your messages in WhatsApp, for example, are end-to-end encrypted. As soon as you hit send, it jumbles up all of the data. So if anybody were to try and steal that data, it wouldn't make sense to them. Okay, it's only when it gets to its destination that it can be decrypted and the actual recipient of that data can read what it says. So we're actually looking at encryption software. Okay, and if you've revised encryption software, we know that it changes data using something called a key. Okay, so that's the first two. Encryption software changes data using a key. If the changed data is intercepted, it cannot be, if we have a look at our options here, it cannot be a part, it cannot be lock, it cannot be understood. Okay, because we know that encryption software changes data using the key into something that is unreadable or not understandable. So understood for our 3rd mark there. Okay, now we're looking at the next bit, which is in a totally different topic. So these are kind of split up into 2 sections here. This is another piece of utility software that the second part of this question is referring to. So something software analyzes the data on a disk to find files that have been split and stored in separate locations. The split files are moved to be something in storage, and the free space is moved together. Okay, so this is describing the process of defragmentation. Okay, when you download a large file and it can't actually fit the whole of that file in a consecutive space on your hard drive because of other files that are in the way. So it needs to split it up into different parts, which can slow down the access of your hard drive because it's having to look for maybe half the file in one place and half the file somewhere else, and they might be quite far apart. So it takes a bit of time to find. This is only on hard drives, so not on SSDs, on magnetic storage. Okay. So we're talking about here defragmentation software. The split files are moved to be consecutive in storage. So defragmentation takes those fragments and it puts them back together. And that means when we open that file up again, the files are together and the hard drive can find it quicker, and therefore it can load it up quicker. So the split files are moved to be consecutive in storage and free space is moved together. This does not provide more storage on the disk. Instead, so it doesn't actually give you more space. It's just putting all the free space together. So when we download something else later on, we can put it straight into that big bit of free space and it doesn't need to be fragmented. So instead, it makes the access of the data faster because the read head does not have to move as far to access the next part of the file. Okay, so think of this as like a record player with a needle on it, but think about the record or the data being stored in different parts of the record, and the head or the needle needs to move to find those bits of data. If that data is all together, the head doesn't need to move as far to get it. Therefore, it's the speed of access of the data is faster. Okay, I think a lot of people for this one would put down speed. Instead, it makes the speed of the data faster. It's not making the speed of the data faster. It just makes it the access of the data quicker because everything is together. So that's your 6 marks for that one. If you're getting 4 or 5 in that question, then that's quite good. But this is a real good opportunity here to get 6 quick marks. Question 4AI is worth 1 mark, and this is just a tick box question. And the questions that come further on down in this particular section will refer to a musician using a computer to make and record music. Part AI is asking us to tick 1 box to identify the correct description of sound sampling. Now, if you do tick the wrong box, you can put a cross in it. That's absolutely fine to do, and then tick the correct answer. You can't tick 2 boxes. So if you tick 2 boxes, then you get 0 marks, as it states here in the marking guidance. Okay, so this is quite a tricky one because there's lots of different terms here that might designed to get you a little bit confused. So I've just put here this sound wave here, and we can see that this kind of gray line here, this is an analog sound. Okay, so this might be somebody saying hello, for example. Okay, so that's an analog sound that you would hear if you're in a classroom and somebody says hello to you. This might be what the sound wave looks like. Okay, what a computer needs to do is take that analog sound wave, which is continuous, and it needs to try and convert it into something digital. So it needs to convert it into some discrete values here. And it does that through a process called sampling. Now, how many samples you have here, and we can see we've got a red line, and a red line. Let's say this is over the course of 1 second. Okay, these first 3. That would be a sample rate of 3 hertz, which means we're doing 3 samples every second. Okay, in reality, we're probably sampling at around 44,100 hertz. So in a normal analog to digital conversion, we'd be taking 44,100 samples of these red lines every single second. So that's the frequency. Okay, so we've got here the frequency of the wave is measured a set number of times each second. Okay, which isn't really true. The frequency of the wave isn't measured. The frequency of the wave is how many times this is sampled each second. The second one says the amplitude of the wave is measured at set intervals. The third one says the digital sound wave is measured a set number of times each second. And the analog sound wave's resolution is measured at set intervals. So it's tried to kind of throw a lot of different types of terminology in here to try and get you a bit confused. What we're actually measuring at set intervals here, and the set intervals is the sample rate or the frequency, is the amplitude of the wave. So where these black dots are here, this is what we're measuring. We're measuring the height of the wave. Amplitude is just kind of another word for volume. So kind of like the loudness of each of the analog wave at these set intervals. So 3 times a second, if this was in 3 hertz, we are measuring the height of the wave. Okay, and what the computer will then do, once it's sampled that, it will then connect these black lines together to try and create a representation of this waveform. And you can see that it looks kind of similar to what we've got. Apologize for my drawing here. It looks a bit similar to what we've got here, but it's not 100% accurate. Okay, so what we've got here with this sample rate is something that would sound like the sound file, the original sound file, but the quality wouldn't be that high because we can see here, for example, we've got a few discrepancies. It looks different. Now, if we were to increase the sample rate, let's say we doubled it and we instead of 3 in my previous example, we've now got 6, well, we'd actually have a point here and we'd actually have a point here. So instead of this going straight to here, we're now creating one that goes like this, which is a bit more similar to the original sound file. Okay, so the point of this really is if we've got a higher sample rate, then we're going to get a more accurate representation of the original sound, which is this one here, because we'd have a sample here as well, wouldn't we? So it'd actually go up there and look more like the original. So the higher the sample rate, the better the quality is going to be, the closer to the original. But the downside to that is that it will take up more data because there's more data in there. It's having to store more zeros and ones and more binary digits. Okay, so the actual answer here is that the amplitude of the wave is measured at set intervals, at different intervals. Okay, let's have a look at question 4AII, and this question's worth 2 marks. We're still on the topic of sound and questions that are referring to the musician recording sounds on his computer. So the question is asking us to explain how changing the bit depth will affect the sound file. Okay, so I've got another diagram here, a slightly different one this time. And we can see the blue dots here refer to the sample rate, and the sample rate is kind of the vertical here. So how often we're sampling the sound, or the amplitude, how often we're sampling the amplitude of this sound. And we can see that these are the same distance apart. So the blue dots are the same distance apart because it's a consistent sample rate. It's doing it a certain number of times every second. Okay. Now the bit depth is how accurate those samples are here. Okay, so for example, let's take a look at this one. So we can see the red line here is somewhere in between 6 and 7. Okay, and the computer needs to determine which one it's closer to. And it's closest to 7, so it will then draw the waveform at 7, when actually it should be at 6.5. That's because the bit depth isn't quite high enough to be able to reproduce this waveform here accurately. If we doubled the bit depth, then we'd be creating another point here in between 6 and 7. And then when this waveform is sampled, that blue dot would actually be right where it needed to be on that red line, which would mean it's more accurate, which means the quality is better. Okay, so that's how bit depth changes the sound. Obviously, if we were to create another increment here between 6 and 7, that means that the sound file is going to have more data because it's physically saving more data into the file. So the file size will get bigger if we increase the bit depth. Likewise, if we got rid of 6 completely, okay, and we only had 5 and 7, then we're using less data. But the effect of that would be that this blue dot would have to go to either 5 or 7, which means that it wouldn't be as accurate, so the quality would decrease. Okay, so for this example here, let's write an example answer. We're explaining how changing the bit depth will affect the sound file. So let's say if the bit depth of the sound file was increased, so if we put an extra little increment here between 6 and 7 to make it more accurate, then the quality of the sound file will improve. Okay, because we're getting a closer representation of the red line here, which is the analog wave, and we're trying to recreate it digitally. So we know the quality of the sound file would improve. Again, but if we've increased it, then we know that we're going to need more data to store within this audio file. So however, this would result in an overall increase in file size. Okay, perfect answer. So we could talk about on these other points as well. We could say the number of bits per sample will change. So there's going to be more or less bits. Or what have we got? There will be a change in the accuracy of each sample, because if we're adding bits, there's going to be a change in the increase. So just bear in mind, this question doesn't say how increasing, or it doesn't say how decreasing the bit depth, which is why I've put that in my answer. If the bit depth was increased, then the quality will improve. If you could write, if the bit depth was decreased, then the quality would get worse and the file size would get smaller. So just make sure you're writing it in the right context. So increase, quality up, file size up, decrease, quality down, file size down. Okay, let's have a look at question 4BI. This one's worth 4 marks. This question says, the musician has run out of storage space on their secondary storage device and needs to buy a replacement. Identify whether the musician should buy a magnetic secondary storage device or a solid state secondary storage device for their computer. So there's really no right answer for your type here. All this question is looking for is that you write the properties that are associated with that particular storage device in your justification. So you can put either magnetic or solid state, and there's no marks available for putting either one of those, but it's with your justifications where you pick up the marks. So let's have an example answer here. So let's say type, and if we pick a solid state, so an SSD, and then all the question is it's trying to assess your ability to be able to identify what the characteristics are of an SSD, which make it suitable for this particular task. And you can see we've got these here down on the bottom of the mark scheme. So we've got a few things to point out here. We can't just say fast. For example, we need to say the fast speed of access of the data. And we can also compare it to the magnetic drive as well. So we could say that the speed of access is faster on a solid state than on a magnetic. Lots of people tend to put on this question that there is, or it's cheaper. So for magnetic, they'll say it's cheaper, which it is, but you need to say that it's cheaper per unit of data, okay? Because you will have some magnetics that are more expensive than some solid states. Those magnetics might be 2 terabytes, for example, and the solid state might be 256 megabytes or something like that. So you have to say that it's cheaper per unit of data. So let's have a look at an answer. So we've gone for solid state here. We need to justify our choice. So we could say the musician should choose an SSD because, and let's go for the first point, which is the most obvious, that they are more durable than magnetic as they have no moving parts. Okay, so that would be 1 mark there for saying that it's durable because it's got no moving parts. So this second bullet point here, mark point 2. We could elaborate on that as well. So the dots here mean that we can kind of go on to explain that point a little bit more if we want to, and we can get a second mark for that one. This point says, so computer can be moved without risk of losing data. If it's a musician who needs to go to different places to record, then the SSD will be better because it's more durable. If he, if he gets bumped around in the back of his car, it's not going to be as susceptible to damage than a magnetic. Let's go on to the next point. So we could say that it's got high capacity. So the SSD also has a high capacity. And then we could explain this as well in a bit more detail, which means that the musician can store more files or higher quality files on their computer. Okay. We also know that the SSDs are smaller in physical size. They're thinner and they're magnetic. And again, if we're talking about things being portable, need to be moved around, then size might come into that as well. So we could also say the SSD is also smaller in physical. physical size, so it is easier to transport. Okay, so that should be the 4 marks there that we need to be able to answer this question. If you feel like you're stronger at talking about magnetic, the properties of magnetic, then you can absolutely put magnetic down as well. Again, there's no right answer for this. It's just about being able to justify whichever one you've picked. And question 4BII, probably one of the most straightforward on the entire paper. It's for 1 mark. Identify one other type of secondary storage. When I graded this paper, there was quite a lot of people that missed this one out, and this wasn't down to them not knowing the answer. It was because this tiny question was placed right at the bottom of the page underneath the last question, which was quite large, so people just missed it. But we're looking at one other type of secondary storage. The answer here is optical. If you put optic, you can get a mark for that as well. But if you put something that's an example of optical storage, like a CD or a DVD or a Blu-ray, you don't get the answer for that, okay? Because that's not really a type, that's an example of an actual kind of piece of optical storage. So optical is the correct answer for this one for 1 mark. Right, let's take a look at question 4BIII. This is a tick box question that's worth 1 mark, and we're looking for the smallest storage capacity in the 4 options that we've got there. And you can see that they are all in different units. The first one is in gigabytes, then megabytes, then kilobytes, and then terabytes. So we need to convert all of these into one common unit. So I'm going to convert them all into megabytes. Once they're all converted into megabytes, then we'll be able to compare them to see which one is the smallest. So I've drew out this table here, and we can see we're starting off with the kilobytes here at the right. Then the next units that are higher are the megabytes, then the gigabytes, and then the terabytes. And all we're doing to get from one to the other is we're dividing by 1,000. So if we're going to the left, we're dividing by 1,000. If we're going from left to right, so to convert terabytes into gigabytes, we'd need to times by 1,000. So it would be the other way. So all we're doing really is we're moving or shifting the decimal point 3 places to the left if we're dividing, and we're moving it 3 places to the right if we are multiplying. So what I'm going to try and do is get all of these different capacities here on megabytes in the megabytes column so we can compare them. So let's take the first one here. We've got 2.1 gigabytes. We're moving to the right, so I know that I need to multiply this by 1,000. So we're moving the decimal point 3 places. So I'm just going to stick an extra couple of zeros on there to make it easier to see. So the decimal point is going to go 1, 2, 3. And we know then that we've got actually 2,100 megabytes in there. And we can see that this one is smaller as it stands. Let's have a look at the next one, which is the 200,000 kilobytes. We're moving to the left, so we know we need to divide. And that means that we are going to move the decimal place, which would be here 3 places to the left, which puts it just there. So this one's 200, and we can see that that is now the smallest. And finally, the one here, 0.0021 terabytes. We need to convert this to megabytes, so we're going to need to multiply by 1,000 and multiply by 1,000 again. So let's convert it to gigabytes first of all and move that decimal point 3 places to the right. 1, 2, 3. So that's in between the 2 and the 1. So that's going to be 2.1 gigabytes. And we can actually see that we've already figured this one out here. And we know that 2.1 gigabytes is 2,100 megabytes. And that gives us our answer. Once we've got them all into this same units, then we can compare them and we can see that 200,000 kilobytes here is the smallest. That's the correct answer for 1 mark. Okay, question 4BIV kind of uses what you learned in the last question to try and solve this one, but it has an extra step in there. So this question is worth 2 marks, and we get 1 mark here for showing our working out, and then 1 mark for putting in the correct answer. So it says the musician's recordings have an average or a mean file size of 3 megabytes. The musician has 1,000 recordings. Calculate an estimate of the storage space in gigabytes that the 1,000 files will require, assuming they are each 3 megabytes in size. Show your working out. So a couple of things we need to be wary of here. The first one is that the file size is given in megabytes and that it's asking for a final answer in gigabytes. And you can see that down here too. The second thing is we're going to need to do some conversion and show our working out when we do this question. So let's first work out what the size is going to be, the total size is going to be. in megabytes. So we know we've got 3 megabytes per song, and we've got 1,000 songs or 1,000 recordings. So we do a bit of maths, and we know that this is going to be 3,000 megabytes. And that is literally all we need here in our working space. Okay, we've done that calculation. It's all we need to be able to get to that 3,000 megabytes. Now we need to convert the megabytes into gigabytes. And we know that if we're going larger, what we need to do is take this and then divide it by 1,000. So we're moving the decimal point from here down three places to the left. And if we did that, 1, 2, 3, we'd get 3.0. So we're actually on 3 gigabytes as our final answer, which you can see is here. Okay, question 5A is worth 2 marks, and moving on to a new topic now. This is to do with the CPU, the central processing unit. This question is asking us to describe what happens during the fetch execute cycle, which may look pretty tricky on the face of it. Obviously, you go into quite a lot of detail about what's happening in the fetch, decode, execute cycle in terms of registers and movement of data and addresses and all that kind of stuff. You don't need to do that in this question. It's actually very, very straightforward. All we need to do is state that instructions are fetched from spelling, fetched from RAM or main memory or primary storage. Okay, that's 1 mark. Instructions are fetched from RAM. We could say by the CPU, we could say. Okay, these instructions are then decoded. That's 2 marks. The instructions are then executed. Okay, so there's quite a lot of clues in the question here for what you need to do. It's the fetch execute cycle. We know at the different stages that instructions are fetched from primary storage or from RAM. They're decoded to figure out what it is they're actually going to be doing, and then those instructions are executed, and then the process starts over again. So that's actually 3. I've got 3 marks there. I would have got 3 marks. If it was a 3-mark question, you'll need to put 2 of those things down. Okay. So there we go, question 5A for 2 marks. Okay, question 5B is asking us to describe what's happening with 2 registers that you choose during the fetch execute cycle. So we need to name 2 registers and then say what their purpose is. Okay, so you can pretty much pick whichever registers you want here. And we do find a lot of students put down here the ALU, which is the arithmetic and logic unit. And that's not actually a register. That's a component within the CPU, which is used by the registers to do calculations. Okay, so don't put the ALU down for this one because it is not a register. So the easiest 2 to pick really are the MAR and the MDR, if you can remember those ones. So my first register is going to be the MAR, or the memory address register. Okay, and we know that this one stores the address of the next instruction to be fetched. Okay, so we could say the MAR stores the address, because it's MAR, memory address register, of the next, or you could say current as well, next instruction to be fetched. Perfect. Okay, that will give us 2 marks for that one. And then the MDR, so the D, we know is the data register, so the memory data register, or our data register, and the MDR stores the actual data fetched from memory. Okay, so they're really the 2 easiest ones to put in there. The ACC, or the accumulator as well, is a good one because we know that it stores the results of any calculation, so that uses the ALU to be able to do that. The ALU does the calculation, and then the result of that is stored in the accumulator. You could also put down the program counter, or the PC, which stores the address of the next instruction to be fetched. And we've also got a couple of others. You can put the current instruction register here if you wanted to as well. Okay, so we've got quite a few options, but maybe memorize 2 or 3 of these, and then put down the one that you can remember the most in your exam. Okay, question 5C is looking at the characteristics of a CPU. We've got 3 characteristics that we need here that can affect its performance. There are usually a few issues with this question. You can see here on the guidance from the mark scheme, usually students don't put down the second part of these characteristics, and they can't get them up because there's not quite enough there. For example, if you just put cache, okay, that the cache doesn't affect the performance of the CPU. It's the size of the cache that affects the CPU. Cores doesn't affect the CPU. The number of cores affects the CPU. So we've got to make sure you're being specific for that one. So we know that the three characteristics we've learned in lessons are clock speed, the size of the cache, and the amount of cores, or the number of cores. And that will get you all 3 marks for this question. Okay, question 6A is moving on to embedded systems. This one's worth 3 marks. We've got a new scenario here. It says a car has a follow me system that uses a cruise control feature to allow the car to follow the car in front of it. It will keep the same speed and distance without the driver's intervention. The cruise control system is an example of an embedded system. Explain the reasons why the follow me system is an example of an embedded system for 3 marks. So we need to think of 3 reasons why this is an example of an embedded system. So what we're doing really is thinking back to our embedded systems. What are the characteristics or properties that make an embedded system, and then applying them into this context. Okay, so we know that embedded systems, first of all, have a specific function, or they're only limited to one function. So we could say the follow me system is an example of an embedded system because it has a specific purpose with limited functions. Okay, we could also say that it's difficult to change the purpose or the function of it. It is also difficult to change the function of the system. Okay, so a bit like a washing machine, for example, is an embedded system because it's difficult to make it do something else. It can only be a washing machine. It can't be anything else. So we can't program it to do other things, really. Okay. We also know that embedded systems are built into larger devices. So we could say that the follow me system is a smaller system built into a larger device, which is the car. Okay, so that should get us 2 marks at the moment. The last point we can get here, we could say that it's got its own microprocessor, it's got dedicated hardware, or we can say it's automated. So I'm going to put the automated one down. It is also, because that's mentioned in the question, automated system. Okay, so any one of those 7 mark points there, 3 of them that you're trying to choose to get you 3 marks for this question, and try and relate it to the context as well, mentioning the follow me system and the car. Okay, 6BI is worth 2 marks, and we're still on the scenario of the follow me system. This one says the car system has read-only memory and random access memory, so ROM and RAM. State 2 items that will be stored in the ROM for the follow me system. So on this question, we're not thinking about things that are going to be changing as the program's being run, because this is in the ROM. It's read-only. We can only read from it. We can't write to it. It's a bit like getting a book from the library. We can look in it and we can read it. We can take that information out of the book, but we can't put any information in it and rewrite the book. So it's read-only. So stuff that's not going to change. So for example, the BIOS. Okay, so the basic input-output system that starts up when the actual system becomes online, and the startup instructions. Okay, so that is all stored in the ROM. And the firmware, which are actually the instructions for the follow me system. So the basic instructions that it needs to be able to operate. Third bullet point here says the example of data being stored, so the maximum speed or the minimum distance. So the maximum speed, meaning this is the maximum speed that the system can go. The car can't go any faster than this. And that would be a fixed amount. This will be a constant, so something that doesn't change when the system's operating, because there'll be a safe speed that the car can go. If the car in front of you that you're following decides to put its foot down on the accelerator and go up to 100 miles an hour, you don't want your car to be following that person. So your car will have something built into it to say, do not exceed 70 miles per hour. It might also have something that says, do not get within this range of the car in front of you. Don't get in within 1 meter. Always make sure you stay at least 10 meters behind it at all times. So that's stuff that doesn't change, which means it's read only, because we don't need to change it when the program's running. The other thing that would be in the ROM would be the operating system of the embedded system. So anything that isn't being changed as the system's running would be inside the ROM. Right, 6BII is worth 3 marks, and this is looking at the other side of the coin. This is looking at the RAM. So we know that RAM stores currently running data and instructions, and we need 3 items of data here that are going to be stored in the RAM for the follow me system. So things that are going to change as the program is operating. And we've got a few examples here. So the current distance from the car in front, we know that that's going to change. Okay, as the car is driving and following this car, it's going to have something on it that's monitoring the amount of distance between the 2 cars, so it doesn't get too close and it doesn't get too far away. If it does either of those 2 things, then the system might not function correctly. We've also got the current speed of the vehicle, so how fast we're going. Okay, we also need how fast the vehicle is going in front, so the data from the sensors to tell us that the car in front of us is going 30 miles an hour. If that car is going 30 miles an hour, then we need to know the current speed of our vehicle. If we're going at 25, then we need to speed up a little bit, 5 miles an hour. So these are things that are changing all the time. We can also include examples from reading from sensors and driver actions. So if the driver in front of us is moving the wheel, or if they're braking, or if we're moving the wheel or braking, and we might have a sensor in there that detects the red lights or the white lights of if the car's reversing, for example. We also need to know the direction of the car in front. So if it's turning, then we need to apply that same kind of turn onto our car as well. So anything that's changing within the program as this follow me system is running will be stored in the RAM, because we know that RAM is volatile memory, so it's able to change, whereas ROM is not able to change. Okay, the final question on this exam paper is 6BII, and it's worth 2 marks. We're still in the follow me system context for this. And it says, explain why the follow me system does not need virtual memory, for 2 marks. So to answer this one effectively, we need to know, first of all, what virtual memory is. And then we need to explain why the follow me system, as was outlined in the previous question, and why it doesn't need it. So first of all, virtual memory is a space that's created in secondary storage to use as additional RAM. We know that this is slower to access than the RAM, but it does mean that we can have more applications and programs running at the same time, but the effect is that they will be slower to operate. And we need to think about why this embedded system doesn't need it. So first mark point here, we can see it says it only stores a small amount of data in the RAM. So we don't actually need much data to be stored within this system. Therefore, it's unlikely that we're going to run out of RAM, because there's not actually that many variables that are happening with this system. Okay, all we really need to know is the distance from the car in front, of how fast it's going, if it's turning, etc., which doesn't really use up that much memory, because there's only a few amounts of pieces of data there. Okay, so they will know that when they make the system. They'll know how much RAM it needs. They'll know how much data is going back and forth between the RAM and the system when it's being used. So they would have built that into the requirements, which is this mark point down here at the end. Dedicated hardware, it will be optimized. The RAM is designed to meet the system's requirements. Okay, so because it's only doing one function, we're never going to need to do anything else. So we know how much RAM we need to put in it, because we're not adapting it in any way. So that's really kind of where we're going with this. Also, the system has no secondary storage. Okay, it's just got the ROM and the RAM. It have an operating system. It's got no secondary storage in there to use. So we can't actually use virtual memory in this, because we don't need it, because we can't use it, because there's no secondary storage to put the virtual memory on. So let's try and get 2 marks out of this one. So we could say the follow me system only stores a small amount of RAM due to the few items of data that are needed. Okay. We could also say that when this system was designed, the engineers would have known how much RAM was required for it to function And because it only does one job, it is never going to need any additional RAM. Design. Good. Okay, there we go. So we've got 3 points down there, which would get us 2 marks. But try and just understand that the need that this has been designed for a specific purpose, and it's not going to need any more RAM than what has been put into the system because it's only got one function, and that's for 2 marks.